begin a new section. This is section 2.6, where we go over some very useful trigonometric limits. These limits here will allow us to compute derivatives, as we will see in a couple of weeks, maybe. In order to to find these limits, to compute these limits, we need a tool that is very useful. And so to compute limits, the first tool we went over were just consisted of algebraic manipulation and appealing to the continuity of a certain function to simply evaluate. Now we are gonna introduce a new tool, very powerful tool, where we don't actually compute things explicitly, but we are able nonetheless to find the limit or to prove that something has a limit based on the knowledge of two functions that bound the expression you want to compute the limit of. So we start by assuming that for some x not equal to c, which we always assume that it lives in some open interval containing the point C in question. So we assume that we have some L of x that is less than or equal to f of x, less than or equal to some u of x throughout this interval. And we also assume that the limit of L of x as x approaches c is known and is the same as the limit of u of x as x approaches c, which is equal to L, some number L. And what we really want to know is what's the limit of f. And so the conclusion here is that, first of all, the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c is in fact equal to L, the limit of L and u, L of x and u. L here, of course, stands for lower, and u for upper. So you have a lower bound and an upper bound, and these two things put together force f of x to converge to the same limit. So visually, again, we have our point C, which lives somewhere here in the real line, and we have the function f. Let's make it a little bit more oscillating so that we have L of x, the function f of x, which is in between, and the function u of x. And this value over here will be equal to L. Okay, so as x approaches c, either from the right or from the left, we see that L of x goes to L, and the same is true for u of x. Since f of x is trapped between L and U, it has no choice but to converge to the same limit, and that's the idea behind it. Here I drew an f that is actually defined at the point C, but for this theorem to apply, we don't actually need that. In fact, the applications we'll make of this squeeze theorem will be mostly relevant when f is not defined at the point. Okay, but nonetheless, u and L are, and they have a limit, and you can compute the limit using the property of continuous functions, when it's just a matter of evaluating at the point. But we cannot do that for f, because f is not defined there. So that's the way we use this theorem. There are some consequences that we'll see at the end, and some kind of questions that you might be asked to solve for exams. But let's now jump to the most important consequences, and that's why this section is called the trigonometric limit. So we have some useful inequalities. So far we've only computed the limits of rational expressions, that is polynomials divided by polynomials, or of continuous functions, as x or another variable approaches a certain value. Now we'll be able to compute trigonometric limits, and the first theorem encodes very useful inequalities that will allow us to do so. We'll prove this after we've gone over the applications. But the first one is that cosine of theta is less than or equal to sine of theta over theta, and also less than or equal to 1, not for any values of theta, but for theta between pi over 2 minus pi over 2 and pi over 2, and theta is not equal to 0. Why are we requiring here that theta is not equal to 0? Well, because this expression doesn't make sense for values, for theta equals 0. So the expression in the middle, and that's what I was mentioning before, so sine of theta over theta, when theta is equal to 0, this expression is not defined. Sine of 0 over 0 gives you 0 over 0, so it's not a well-defined expression. Okay, and as I said, we will prove the following a very important limit using the previous theorem, and we'll obtain it as an application of the squeeze theorem. Actually, this is immediately telling us, if you look over here, what are the functions L and U. So L of x, or L of theta in this case, will be cosine of theta, and U of x will be the constant function equal to 1 for all theta. Okay, so that's the first application. And this will allow us to compute the limit of sine of theta over theta as theta approaches 0. And the second one is a related limit. Now, that has to do with the behavior of cosine of theta when theta equals 0. You know that cosine of theta, as theta approaches 0, approaches 1. But we want to know what happens when we divide that expression by theta. Because, this is a limit that will appear when we're computing derivatives. of sines and cosine. So the main theorem here is, which are the very important trigonometric limits. We said there are two of them, one for sine and one for cosine. First one tells us that the limit as theta approaches 0 of sine theta over theta is equal to 1. And the second tells us that the limit of 1 minus theta, 1 minus cosine of theta, divided by theta, as theta again approaches 0, is equal to 0. So these are two limits, and we'll derive the first one, the limit involving sine, using the previous theorem and which we'll prove at the end. And the second one will just be a simple consequence of the first one. So let's try to go over why this is true. So proof of that for A, we know, thanks to the previous theorem, that cosine of theta is less than or equal to sine of theta over theta, and is less than or equal to 1. And so this is going to be our L of theta, and this is our U of theta. And this expression here is f of theta, the expression in the middle. Now, notice, so we know this is just an observation. Note that f is not defined at theta equals 0. As we've been talking about from the beginning of the semester, that will not prevent us from computing the limit. There will be a trend. It's just that we won't be able to evaluate at the point, but as we approach the theta equals 0, this quotient here, sine theta over theta, will be approaching something. Something happens to be 1. So when we apply this squeeze theorem, we notice that the limit of L of theta, which is one limit that we need to have as theta approaches 0, is equal, well, by definition, L of theta is simply cosine of theta as theta approaches 0, but cosine is continuous everywhere, in particular 0, so when we compute this limit, it suffices to evaluate at the point. I mean, this amounts to evaluating theta equals 0, but cosine of 0 is equal to 1. But 1 is also the limit of u of theta. Remember the u of theta, as theta approaches 0, u of theta is equal to 1, just a constant function y. So we have checked the hypothesis of squeeze theorem, and this allows us to conclude. So both L theta and U theta approach the same limit theta approaches 0. And so this allows us to conclude then that what's in between the two functions approaches the same limit. So the previous allows us to conclude that the limit theta approaches 0 of f of theta, which is the same as the limit of sine theta over theta, if theta approaches 0, is equal to 1. This is a limit that we didn't know how to compute before, but now thanks to the squeeze theorem and this inequality that we are going to derive in a few minutes, have allowed us to find a new limit. It's not of a polynomial type or using continuity of functions. We use continuity of the lower and upper functions, but not of the function in the middle, which is the one we're interested in. And in fact, we cannot use continuity because the function is not even defined there. Okay, so that's one of the consequences of the squeeze theorem. We can remark when we are applying the squeeze theorem. So if we have that L of x is less than or equal to f of x less than or equal to u of x, we will often write then that the limit of f of x, so the limit of L of x as x approaches c is then less than or equal to, we take the limit on both sides, so limit c u of x goes to c. It's like we take limits on all sides, and if this is L, this is L, this implies then that the limit of f of x as x approaches c is equal to L. So that's one way to write it, or simply this is all acceptable. And we simply draw an arrow pointing to this approaches L, goes to L. This approaches L as x approaches number c. And so these two things together imply what the limit, again, the limit of f of x as x approaches c is equal to L. Okay, so that's the first thing. So, so this matters of notation, how to write the conclusion, final conclusion when you're applying the squeeze theorem. And yeah, and since we've gone over the first application, which is computing the limit of sine of theta over theta, theta approaches 0, we can now move on to part B of the theorem, which we'll do in the next video.